Yeah. Oh, okay.
Yes, maybe.
Yeah, yeah, this one. Yeah.
Here also you can see the end.
Oh, even here as well, you have two lines. Oh, no, no, no. Okay.
So I will do it later. We will run solution in your laptop.
Okay, okay, we can do that.
Yeah.
Uh, okay, okay, okay. I will unshare this.
Mm-hmm.
Uh,
I'll watch the recording and I will do it.
Yes, yes, yes. Actually, I forgot to
Yes,
record
it's a
for the
waste of
second
time.
meeting. Yeah, yeah, I forgot to record for the second meeting. So I will just show you this first meeting. In first meeting, we did the geometry, no?
Yes, yes.
Yeah, so geometry will be made, and I think mesh you will remember. I will in this recording, I will just show the mesh for the review. Okay,
Okay.
all the settings. So I will share my screen right now. Okay, so this is the mesh. This was the face meshing, 7 faces. Firstly, these 7 edges were selected: 1, 2, 3, 4, 5, 6, and 7. Okay, and
Yes.
150 divisions, and 1.75 was the bias factor. And edge
Yeah.
sizing 2, these were the 4 edges: 1, 2, 3, and 4. And divisions were 100, and bias factor was 1000. And this was 4 edges, these two edges, and these 2 edges. So
Yes,
this
yes.
division was 300, and the last edge sizing, no, no, second last was this 4 edges, these 2 edges, and these 2 edges. This.
Yes.
So there were
Yes,
100
yes.
divisions, and lastly, this very small
Trailing
thing,
edge.
yeah,
Yes.
this 2 edges, and we just gave this a 50 divisions.
Yes.
And name selections, we every other boundary except the outlet, we named it as inlet. You see,
Yeah.
every
And the
boundary
outlet.
we put it inlet, and outlet is these 3 edges. Don't forget to
Yes,
select the
yes.
small edge.
Mm-hmm.
Okay, so yeah, I will just update the mesh if I haven't already. Okay, it's yeah. Okay, you can share my screen correctly, right?
Yeah.
So in this NASA, they use this as incompressible flow. If you just there is something, yeah, here you can
This
read
Mac
this.
number is given.
No, we will ignore the mark number. Actually, we just need this Reynolds number. Mark number is actually
Okay,
not
6
correct.
million.
Actually, yeah, yeah.
Okay.
So we will just use this. Reynolds number is correct. So yeah, here you can see that data provided for comparison for this particular, it's essentially incompressible.
Hmm.
Okay, so what solver we will use?
Pressure based.
Yes, pressure based only. And models we will leave energy as off only. And okay, we are validating it for Spalart-Almaraz scale.
Spalar. Yes.
Yeah, so
Exactly.
SA model, and you can choose this, but there won't be any difference. You can actually try both of them. There won't be any difference.
Hmm.
So okay, for now we will use this strain voltage based. Okay, is my recording going on? Yeah, my recording is going on. So okay, so for the materials, I will just leave it as it is. We don't need to convert it to ideal gas.
Okay.
Okay, and boundary conditions only. Yeah, this will be the velocity inlet. The main thing that you have to do is yeah, change this to magnitude and normal to boundary now. Change this to magnitude
Hmm.
and direction. Because what will happen
Okay.
is what this normal to boundary means, this we have considered it as inlet, this even these walls. So flow will
Yes.
be normal to the boundary. The flow will be coming in this direction, not in
Yeah.
this direction. Okay.
Hmm.
And from this also, this is
Exactly.
a C-type measure. Flow will be in this direction, not in this parallel direction.
Mm-hmm.
That's why,
Yes. So
yeah,
we have to change
yeah, magnitude and
magnitude and
direction.
direction.
Yeah, and velocity will be whatever we computed. Yeah, here for 6 million.
Yes, 87.64.
Yeah, so I just copy paste it here.
Yeah, yeah.
Yeah. So and yeah, this what is this turbulent viscosity ratio?
No.
It is actually the ratio of laminar viscosity to the turbulent viscosity. So since we are assuming the flow is completely turbulent, we can take this viscosity ratio as 1. Okay.
Okay. Yes.
So I will just take this as 1 and okay. Okay, that's all we need to do for the boundary conditions. We will keep everything the same, even the operating conditions we won't change because everything is done at 1 bar only at sea level only.
Okay.
So reference values you can check. है ना?
Yes,
So
yes.
this is the density and viscosity and velocity.
Velocity,
This,
yes.
yeah, from this we obtain this Reynolds number. And methods, yeah, make this as coupled and second order. And
Second order,
only
yes.
pseudo transient. Yeah,
Hmm.
only pseudo transient. Controls will remain same. We don't edit these. And okay, report definitions. Okay, so
Left and
firstly,
right.
yeah. Okay, I also give you this homework. You know what should be the area and 3D case? You know?
Yeah, you have given. I have searched, but I couldn't find it.
Okay. So for the 2D case, it would be equal to chord length only. So chord length is 1 meter. So I will just leave it as 1 meter only. So because I will tell you later what is it for 3D case.
Okay.
So now we will
Yes.
just make this drag and lift report to validate the data. CD, I will choose all three edges and track coefficient. Just select all of three. Okay. Similarly lift. Oh, this is moment. Okay. Okay, we have the report definitions. And monitors, actually, this won't matter in this case. We can untick everything, or we can just do this like this, none. Okay, so initialization, I will choose standard only. And I will just run the calculation. I think it will take like 500 iterations. This is a very easy case, and the mesh is also very good. So we
Yeah,
can just do
that's
this.
why it will converge definitely.
Yeah.
Maybe.
We will check the convergence by checking this CD and CL values. The scale
Yes.
residual will not come down, not too much.
Yes. In the meantime, you can tell me in the 3D case what will be the value.
Yes. So in 3D case, that area is actually equal to the frontal area or the cross-sectional area. Okay, actually,
Okay.
I cannot show you visually. Uh, Let me try. No, I cannot actually show you visually. Let me check this on Google. Uh, yes. Mm, This would be better understood if there are any visual diagrams. Yes. So here you can see this is the box. This is
Yeah.
the box. So in this case, the flow is going from left to right, right? So the flow, the area which is contacted normally by the flow, which is this area,
Yes.
right? This edge, this face.
Yes.
Yeah. So we will just area will be equal to this, whatever the area of this face only.
Yes. Yes. Square.
Okay, in reference area. Yeah. Let me check other diagrams as well. Actually, I had one picture. Yeah. Suppose this square is kept like this. Okay, so the area would be equal to yeah, the area of this
Rhombus.
surface plus this area of this surface. है ना? Because
Yes.
that's
Got
the
it.
only place that is projected directly to the flow.
It
So
depends
whatever,
upon the geometry.
yeah. So
Frontal
whatever
area.
is the yeah. So whatever is the area that is being in the way of flow, na, which is normally struck by the flow.
Okay,
So,
yes.
yeah, the phase, the flow, whatever the phase that is being struck by the flow normally,
Yes.
that's the area that will be the area of the phase in the reference area.
Okay.
Yes, actually there are no better pictures. I had one very good picture. If I get it, I will send it to you on WhatsApp only. Okay.
Yeah. Sure.
There you will understand it perfectly.
Yes.
Okay. Yeah. So that's what the reference area is about. Yeah. Here you can see that it's converged.
Yeah,
Clearly
it is
converged.
converged.
Yeah. So okay, what the main thing is? Yeah. Check out the CD and CL values. You see, it's CD is 0.00825.
Yes.
Okay.
Negative CL.
CL
Yeah.
is almost zero because you can see it's E minus 6.
Yes.
So that can be considered like almost
No
zero.
lift, yes.
Yeah. In symmetric, you know,
Because
at,
there
yeah,
is
at
no
0 degree
angle of
angle of
attack, so
attack.
lift will be zero.
Yeah. You know that already. So CL can be considered almost zero and CD as 0.008. Okay. So
Yeah.
now we will check these results in the NASA. Here, you can see the CD at alpha is 0.008.
Yeah. We
Yeah.
got the same.
So our drag results are validated at alpha equal to 0. And even CL, yeah, check this CL, they haven't mentioned that exact value.
Yeah,
So it is just
approx. That's why, yes.
Yeah. Okay, so our results are validated also. We just run it for some more.
Now we will do for 10 degrees and 15 degrees.
Yeah. Actually, do this yourself, okay? Because now you already know how to do that at different angles of attack as well.
Yes.
Okay,
So
if
please
no,
share this link in the group.
yes, I will. Okay, let me share it right now only.
So that we will do it.
Yes, just wait a minute. This is the validation. This is actually the main. Here there are validation tests for different turbulence model as well. You can see SST
Yes.
and SST transition SST is also there. KKL model is also there. K epsilon. If you want to, you can do it on these as well. Okay.
Yeah.
And actually, not only for NACA 0012, there are many you can find, like even for, let's see, 4412 validation. Okay, just type this and you'll
Yes.
see these first two websites only. So on this NASA website, there are actually for many airfoil sensors.
It's a cambered aerofoil, right?
Yeah. This is a cambered airfoil, of course. You can tell it from this 4412 thing as well. I think you have studied what
We
this
will check it for
4412
similar
means.
case.
Yeah, I think you know what this 4412 means, right?
Yeah. Yes.
Yeah. Okay. So yeah, just click on this essay and you will get this validation for essay here.
Okay.
ACL is 1.72, CD is now.
Yes, got it.
Other airfoils as well. And okay, I will just
Yes.
stop this calculation because you can see that CD and CL are converged. They are not changing.
Yeah.
You know?
Yeah, they are almost converged, yes.
Yeah. And here the final value, okay. Either you can check this final value, or if you want to print
Yeah,
it.
in forces we can. Yeah.
Yeah, you know how to do it, right? From report application,
Yeah, I
you
know.
can do it. Just click on this CD and you can use this compute. And CL.
Yeah, yes.
Yeah, I think I told
It's
you this
visible
also.
on this.
Yeah.
Yeah.
It's visible. Yeah. So here you see it's even in a
It's
minus
almost
8.
zero.
Yeah, it is to minus 8 also.
Approx, yes.
Yeah, so it will be 0 and CL is this. So okay, I will just end the meeting right now and I will share both of the recordings. Okay.
Okay, bro.
Okay.
Thank you.
Okay, no problem.
Thank you, bro. Bye.
Yeah, see you. Bye.